Good afternoon, ladies and gentlemen. Welcome back to our conference. In this afternoon, our first invited speaker is Dr. Anthony Liang. Dr. Liang is an associate professor in the civil and environmental engineering and the associate director of the geotechnical centrifuge facility at the Hong Kong University of Science and Technology. His research expertise is on saturated soil-plant interaction with emphasis on geotechnical engineering applications, such as slope stabilization. Dr. Liang has published more than 80 SCI journal articles in the subject of soil vegetation in action and co-authors of a textbook, Plant Soil Slope Interaction, published by Taylor and Francis. And Dr. Liang is awardee of the 2022 Outstanding Young Geotechnical Engineer Award of the ISEGGD and 2019 Excellent Youth Scholar of the NSFC. Today, his topic is exploring shear strengths and isotropy.
Right, thank you, Professor Chen. Can you hear my voice?
Yes, it's okay.
Right. Now, can you see the screen?
Not yet. Oh, okay, we can see the slides.
Right. So I can start now, yeah? Right, so good afternoon, everyone. Thank you for the introduction. And also thank you very much for the conference organizer, especially Professor Tang and also Professor Chen, to invite me to give a talk today. So the topic of my presentation is exploring shear strength and isotropy of rooted soils. So this is the outline of my presentation. I will just give you a very brief background on how vegetation could possibly affect slope stability. So then I will identify several key scientific questions that we have been asking and try to define some objectives to address the questions. And then I'll share with you some recent experimental findings on the shear strength and isotropy of rooted soils, and then try to model it theoretically. And then based on what we learned from the experiments and the modeling, we will try to discuss what is the implication to the design of our slope stability. So vegetation is a kind of a nature-based solution that we can adopt to upgrade our slope in a sustainable way. So using this approach is environmentally, ecologically friendly, and of course, it is very pleasing to see it in urban areas, and it could, of course, enhance the biodiversity and also the ecological restoration and have a lot of carbon offset beneficial effects. But from the engineering perspective, perhaps vegetation can be used as a tool to upgrade our slopes. So mechanically speaking, the plant roots could reinforce the soil to grade the soil in especially the shallow region to improve the slope stability. And hydrologically, a plant actually will transpire. And during this process, soil drying, which in effect is to increase the soil matrix suction, could also increase the soil strength. So the talk today, I will focus mainly on the mechanical effect to explore further how that root reinforcement would be beneficially used perhaps in the slope stabilization problems. So if you look at the slope stability design, we can possibly define a failure slip like this. So along this failure slip, actually, the major and minor principal stresses of the soil is rotating along this failure slip. And the reinforcement effect by the root is actually depending on the relative orientation of the root and also the direction of the major principal stress. So in other words, if you have a given root distribution, depending on the position, the root reinforcement effect could be different because the major principal stresses is rotating along the slip surface. So we ask the question, what is the stress path effects? So as you can see in the screen, the failure slip here, we have different type of soil shearing mode. So very commonly used method, direct shear box testing has been used for evaluating the root effect. But if you look at the soil elements near the crest and near this toe, they're actually experiencing not the direct shear condition, but triaxial compression and triaxial extension. So what would be the effect of stress path on mechanical behavior of rooted soil? And do we have any generalized failure criterion to describe the root effect on the slope behavior? So we dig into the literature and look at what's have been developed in the last 20 or 30 years. So as I said, most of the study are focusing on the direct shear box testing. So most of them found that the cohesion of the soil would be increased because of the roots, but the friction angle remained largely unchanged. So only a few studies showing that the roots would change both the cohesion and friction angle. So those are for the direct shear test. But we do have some literature looking at the triaxial behavior at compression and extension. So they do find some changes in the friction angle and cohesion too, but not a lot of studies. So we still find a lot of research gaps focusing on how the stress path would affect the shear strength parameters, including the dilatancy of the rooted soil, still remain unclear. So talking about the failure criteria, we have several models available to capture the root effect on reinforcement. One of the very famous models is the Wood and Warden's theory, which assumes all the root will break at the same time during the direct shearing mode. We do have also the fiber bundle model to improve the assumption for the Wood's model by allowing the progressive failure of the roots rather than simultaneously failure of the root. And if we allow for a more expensive numerical simulation, there are some finite element approach using PY technique that could model the root soil interaction in for slope stabilization purposes. So none of these models have the ability to capture the anisotropy, potential anisotropy problem for rooted soil because of the different orientation of the major principal stress and also the root orientation. And there's no theory developed to address this anisotropy issue. So based on this, we developed several objectives. First of all, to study the effects of stress path, including compression and extension on the shearing behavior of rooted soils. And we try to compare the shear strength parameters obtained from different stress paths. And based on experiments, we hope to develop a model to capture the shear strength anisotropy of rooted soils. So we use the triaxial testing system available at the Hong Kong University of Science and Technology. And the soil we use is the local soil called completely decomposed granite, which basically is silty sand. And we compact the soil to a degree of compaction of 80%, achieving this dry density, which is suitable for plant growth in the urban area. So this is the dimension of the triaxial samples we have been using. So after testing, we open up the samples to look at the root distribution using a scanner so that we can better inform our modeling in the later part. So we perform a very standard triaxial test, actually, a drained and undrained shearing under different confining pressure so that we can obtain the friction angle and cohesion. Okay, so we also compact the sample to different initial density. We follow a very classic or typical test procedure for triaxial testing. First, back pressure saturation, and then drain consolidation to a given confining pressure. And then we shear at a relatively slow rates to achieve a drain condition. And also we perform undrained shearing as well. So I'm not going into details on this testing program, but we focus on different stress paths under different drainage conditions. So this is the typical results obtained from a normally consolidated source. Oh, by the way, in the table here, we also investigated different over-consolidation ratio as well. So the OC effect also be covered. But today, I will just focus on the normal consolidated behavior. So here is the stress strain curve, Victoric stress versus Victoric strain of bare soil and rooted soil, both in normally consolidated condition. Okay, so what you are seeing here are a set of stress strain curves for bare soil under compression. So if I superimpose the result from the rooted soil also under compression, quite surprisingly, you see the shear strength have been reduced by the roots. And one reason is because we introduce, as the root growth in the soil, we introduce interfaces between soil and roots. And actually, the interface friction between the root and soil is much lower than soil and soil interaction. So that's explained perhaps why the shear strength of the rooted soil reduces along compression. So along the extension, this is the result you can see for the bare soil. And if I again superimpose the result from the the rooted soil case, and you see apparently a very small increase in shear strength. Now, although visually it looks a small increase, but if you focus and enlarge the scale here, the increase actually is quite a lot along extension. One thing, sorry, I forgot to mention is the species we have been using is the vetiver species, which is a deep-rooted species, which their root orientation mainly grow vertically, just like one of the pictures I showed you earlier. They like to grow vertically rather than laterally. So that also is very important information when we study the anisotropy, because the root orientation is has an effect to the orientation of the major principal stress that affect the anisotropy. So we observed quite interesting results. So if you look at further on the shear strength parameters, which means the friction angle and cohesion. Now, if you look at the compression first, you can see that the rooted soil has slightly lower friction angle than bare soil. So I already explained that because of the creation of many soil root interfaces. But if you look at the extension here, the friction angle also reduced for the root by the rooted soil, but the cohesion increased very significantly. You can see from 0 for the bare soil to something like 22 kPa for rooted soil in the extension, right? That's what I just mentioned about the conclusion from these shear strength parameters. So in other words, the rooted soil behavior is stress path dependent. In other words, is anisotropic. So to capture these experimental findings, we try to develop a generalized failure criterion to capture this interesting behavior. Now, in our experiments, we didn't observe any breakage of roots. So we couldn't use the philosophy or the assumptions made by the previous root reinforcement model by Woos, by the fiber bundle model. So we have to assume all roots were not broken during the shearing. And one further assumption we need to make is the stress and strain are coaxial during failure. And the root effects on the soil anisotropy can be described by an equivalent microstructure root network tensor. So I will introduce that later. And another important assumptions we made is the cohesion and friction angle are independent of confining pressure. Now, I understand this is, I acknowledge this is quite a simplified assumptions, but then it's a very first model to develop. So we believe this would be easier or convenient for the development of our models. So with all these assumptions, we try to define two fabric tensor. So this tensor here, I wouldn't go into the details of the mathematics, but it is to capture the soil microstructure without any roots, just on the soil structure itself for the bare soil. Then we propose a new fiber anisotropy for root network to describe the root distribution. So as you can see, the mathematical form is similar or actually the same as the bare soil fabric tensor, but using different parameters to capture the anisotropy or the microstructure because of the root network development. Okay, so we do have a lot of parameters, the eigenvalues, the mean values of the eigenvalues of the defectorial part of this matrix. So those are the necessary parameters to need to be calibrated for the modeling. So talking about the failure criterion, we adopted this Masuoka and Nakai isotropic, the spatially mobilized plane model. So this equation is to describe an isotropic soil, talking about the stress ratio or shear stress and the normal stress. So what we did here is to modify this isotropic failure criterion to be anisotropic using Kong et al. 2013 approach. Basically, is to project the microstructure tensor onto the direction of the generalized loading direction in that particular form. So in other words, you can see this eta, which is an anisotropic parameter to describe the soil microstructure. So we can further break it down using the previous matrix I showed you like this. So what we did further here is to propose another anisotropic parameter for rooted soil. So if you compare that two equations, I have another additional term there to describe the effects of root network. Okay, so with this anisotropic parameter, we can then capture the anisotropy in this SMP model. Okay. However, as I showed you earlier, the rooted soil is cohesive. Now, this Masuoka and Nakai failure criteria is for frictional material without any cohesion. It couldn't be perfectly model our rooted soil because it is cohesive, especially in the extension path. So that's why we adopted, we further expanded the formulation using the Masuoka et al. 1990s model, considering cohesive soil. So you can see the mathematical form is quite similar. Actually, it's just a transformed stress tensor so that mathematically is the same, but we have an additional term called bonding stress to capture the cohesion effect. Okay, so we then again modify this bonding stress by taking into account the root effect on the anisotropy to the soil. So these two red equations over there are the new development considering the root effect on the isotropic consideration of the soil microstructure, but also the anisotropy from the root network for the bonding stress. So now we have the mathematical model to describe the anisotropy of rooted soils. So after calibration against our triaxial test data, so on the right-hand side, you can see this is a divectoric plane of the failure envelope for different type of soil, the bare soil and also the NC rooted soil and OC rooted soil, taking into account anisotropy. So you can see here, the failure envelope for the rooted soil is always bigger than bare soil. That makes sense because the soil is good, the root is reinforcing the soil, right? But interestingly, you can see in these two planes, actually the root reinforcement is more important than other planes. So as an implication, so as an engineer, you want to put your plant near the region where you have the stress path following section 3 and 4, so that the maximum root reinforcement can be achieved. So one important information I want to highlight here, in the literature, we found the direct shear box scenario, the friction angle didn't change much. That makes sense from our modeling because you can see the increase in friction angle here is only linked to in this section 1, which represent the direct shear stress path. But if you look at the triaxial and extension path, the increase in friction angle, or the change in friction angle and the change in cohesion are much larger. So our model also can capture the direct shear loading conditions. So this is could be quite generalized envelope for rooted soil.
Dr. Liang, you have 4 more minutes.
Right. Okay. So that would be my 2 last slides.
Oh, okay.
Sorry. Yep. Right. So we found that can also affect the friction angle, not only the cohesion as typically found in the literature. And evidently, root reinforcement effect is anisotropic and path dependent. For deep-rooted soils, for deep-rooted species like the vetiver, we were investigating soil reinforcement along the compression curve was much less than that along the extension curve, because the major principal stress in the compression almost parallel to the root orientation for the vetiver. But if you have an extension, they are perpendicular to each other, so the root reinforcement effect will be much more significant, right? So that demonstrates the anisotropic effect. So yeah, root can mobilize the tensile strength much better along the extension path. So coming back to our engineering problem, what one advice we could take is assuming friction angle to be unchanged by root may not be always true, depending on where the slip position we are talking about. For direct shear position, yes, maybe you can assume zero and nothing changed in the friction angle. But for the crest and the toe, the friction angle could have been changed by the root. And if you select a species with a deep-rooted species, we would advise you to put it near the slope toe, because at that position, extension is the more preferred failure mode. So the reinforcement will be more significant. So by the same token, if you have a laterally rooted species, you could put it near the slope crest, because at that position, you will have a perpendicular direction between the major principal stress and also root orientation. That will give you the highest root reinforcement effect. So strategically, we shouldn't put only one species along the slope for slopes for soil bioengineering applications. We should be smartly considering soil mechanics to arrange our species to maximize the slope stability effect. So all what I've been just talking are based on these 3 publications. So they are all already published. So if you're interested, you are more than welcome to take a look. And I also acknowledge my student, Ali Akbar, who have produced all this very interesting work for this presentation. So that's it for my presentation. Thank you very much. And I welcome any discussion. Thank you.
Thank you, Professor Liang, for giving us such a wonderful talk. And we still have 1 minute. Maybe for our audience, do you have questions? Want to ask Dr. Liang? And it's such a good chance. Do you have some questions? Okay. I have 1 question.
Yes.
Senior. I'm wondering whether when you consider the root effect, where you consider it's a real life one or just a dead root, where you consider the effect.
Well, the root is alive. We grow it in our nursery for 6 months, and then we chop, the top part, and then move it back to the lab for testing. And all these tests are fully saturated, so we didn't consider any suction effect yet.
Okay, thank you, Professor Liang. And our next speaker is Professor Jing Wang from Shandong University. The topic of her speech is intelligent identification and evolution tracking technology of damn hidden disease based on UAV. Hello, Professor Wang.
Good afternoon, everyone. I'm Wang Jing from Shandong University. My report is Intelligent Identification and Evolution Tracing Technology of Damn Hidden Disease based on UAV. My report includes 4 parts. The first one is research significance and the general idea. China is one of the largest countries in transportation and irrigation works, which include many dams. Meanwhile, frequency occurs of serious disasters resulting in significant losses. Leakage and breakage threaten the safety of the dams. Disasters are highly irregular in time and space, which are difficult to forecast. Regular inspection of dams is an effective measure to prevent disasters. UAV-based automated inspection has become a major issue of research. It can automatically collect image of dams and recognize diseases in the image. To realize intelligent inspection of dams, challenge 1 is this and other plants in the dam are abandoned, resulting in the leakage area are likely covered by them, and the leakage is easily failed to be detected. Meanwhile, weeds and other water-bearing vegetations around the dam cause lake-like. It leading to a high probability of negative warnings. Challenge 2. The image collected in multiple inspections have failed deviation. Challenge 3. Data collection methods are single. The data rely on manpower is in a low level. The second part is identification of seepage defects. The dual pass dam's seepage identification method that combines infrared image and low temperature features achieved accurate seepage identification and vegetation occlusion and lush vegetation interference. This is vegetable occlusion. This is lushing vegetations. We design a network. It includes main paths and occlusion paths. It includes maximum pooling layer and low temperature feature function module and calculational attention module, and the network output is seepage identification results. This is low temperature function module. This is the convolution attention module. Attention extraction from the channel dimension and attention extraction from the spatial dimension. Data were collected from the Anjing reservoir and Gongjiazhuang reservoir. Pixels that match the seepage temperature are marked white. It has high weight. And others are marked black. It has low weight. This is the explanation. This is the image. This is my result. This is the leakage, and this is my result. The IOU is 78%, and the depth is 87%, and it has no overfitting. The third part is the damage involution tracing. The first step is faster identification of damage. For the problem of high noise caused by weather, light, and other environmental factors in earlier in UAVs, a fast recognition method based on rich scale convolutional neural network for damage is proposed. Integrating the idea of the REST, combining the RESTnet module and the SE module into the UNet module. The designed SE ResetNet module replaces the convolution blocks used in UNet module. The SE module can learn global information to selectively emphasize useful features, suppress background noise, fills damage low-level detail features with high-level semantic features, and improve the recognitive accuracy of small size. This is the experiment. This is H is the result. The second step is damage involution tracing. The UAV route is not fixed in multiple inspections, and the camera angle and the height are not constant. Correct are small sized targets under the inspected field of view. No target interference such as power line and vegetation are commonly present. A novel deep neutral network named CaroTroNet was proposed, which integrated and improved ST module along with the DLT algorithms to achieve registration of feature offsets. The encoders and MSCF units are introduced to enhance the ability to identify small cracks, forcing the network to focus on the target region and capture target information at a different scale. Collected and still provides the damage variation tracing method with embedded rich scale feature extraction and spatial information. Solving the problem of identifying the time-shifted features of damage under the conditions of view deviation and small target size. Green is the damage change. This is the orange damage. This is experiment include third inspections. This is the first registration. This is the tracking the registration. The green is the change. The first path is the hardware system development. We development of 5 eyes. It includes a laser radar, 3 visible light camera, and 1 infrared camera. This is the ground. It consists of flight control unit and image acquisition unit. This is the ISEGGD cam. This is the intelligent inspection software platform for dam defects. This is UAV data acquisition. This is inspectors. This is data upload and transmissions. This is silver. The mainframe consists of front end and back end. The interface includes navigation bar and display operation area. The inspection task list includes task status and task priority. This is the inspection task management. This is the inspection area. This is the flight monitoring. This is the flight parameters. This data upload. This is the result summary. It includes identifies the image position and the leakage area in the finger. Mark the leakage location on the map. Display leakage identification result. That's all. Thank you very much.
And you say 2 minutes for us. And for our audience, do you have some question? Want to ask Professor Wang? Okay, no question. Thank you again, Professor Wang. Thank you. And our next speaker is Professor Zhengguang Wang, University. The topic is Geological Structure Subsurface Defect Intelligent Interpretation based on ground penetrating data using deep neural networks. Let's welcome Professor Wang.
Okay, can you see my screen?
Yes.
Okay. Good afternoon, everyone. Thanks for this opportunity. I'm very grateful and honored to have this opportunity to deliver a presentation here. My name is Wang Zhengfang. I'm from Shandong University. The title of my talk today is Deep Learning-Based Ground Penetrating Radar Interpretation and Internal Structure Defects Intelligence Inspection. My talk includes 5 parts. I'm going to start with a background and motivation. In recent years, a large number of tunnels has been constructed and operated, especially in China. During the operation period of those tunnels, the structural defects affect the safe operation of the tunnels. Some of the defects, such as cracks, spalling, can be seen visually, which is called the surface defects, while some of them cannot be seen from outside, like the holes, the separation, or void. This is called the subsurface defects or internal defects. This slide shows some accidents caused by the structural defects during the operation of tunnel. Some of the examples, like the collapse of Sasuke Tunnel in Japan, the block falling of Boston Tunnel in the United States. Those accidents also happens in China. Inspection and diagnosis of the internal structure defects should be a priority for safety and economic reasons. Compared with the traditional inspection method, which is labor-intensive and time-consuming, the automatic inspection and diagnosis are expected to replace the human work and have received considerable interest in recent years. So in this talk, I will introduce some development regarding internal structure defect intelligence inspection technologies. Then I will move to the second part to tell you something about the robotic inspection system. In order to realize the automatic inspection of the turn line, one issue should be solved is how to automatically manipulate the GPR. Due to the complex surface of the terminal and the inventable bending on the routing, usually the GPR cannot properly attach on the surface and automatically scan along the surface. So it's difficult for us to collect the high quality data. In order to solve this issue, we developed the robotics inspection system. I will first introduce some fundamentals of GPR. GPR stands for ground penetrating radar. It's not ultrasonic radar, not LiDAR, not INSAR, not STAR. It's widely used non-destructive detection techniques for the subsurface defects. The GPR usually has a transmitter and a receiver. It transmits a high frequency electromagnetic waves to penetrate through the subsurface structure. The wave transmit at different media has different speed, which is presented by dielectrics. When the signal returned to the antenna, we recorded a two-way travel time and the amplitude of the signal to form a B-scan like this finger. Then from this B-scan, we can interpret what is the defects and where is the defects. Also, we can reconstruct the dielectric distribution of the structure to be detected. Then we have developed our own GPR device. It is a compact GPR device, integrated control unit and the antennas. This guy can be equipped on robot arms for automatic inspection. We utilize the robotic arm to manipulate the GPR to scan along the terminal surface without obstruction. The key technologies we have developed an adaptive control method to adjust the distance between the GPR and the scanned surface based on the information collected by the multiple laser displacement sensors. Then the system can adaptively adjust the GPR for the surface with complex shapes and for the routing with complex curves. We have developed the terminal inspection robot, which was equipped with a GPR and a linear scanning camera for automatic inspection of the surface and internal defects being applied. Then I will go I will introduce the dielectric property inversion. As we can see from the finger, that the GPR collected reflected electromagnetic signals rather than the actual shape of the defects. So the reflected echoes are not specially aligned to its actual shapes. So the problem need to resolved is how to reconstruct the dielectric distribution, or we call it the permittivity value distribution from the GPR data. In order to solve this issue, we developed some deep learning-based dielectric property inversion methods. Firstly, we developed a deep learning-based inversion method and designed a new deep neural network. We call it the GPR-InverNet for permittivity distribution reconstruction and complex defects imaging from the GPR data. Specifically, we designed a trace-to-trace encoder to enhance the feature of each GPI trace, using the information from its adjacent traces and form what we call an enhanced trace. With this enhanced trace, the relative permittivity that is specially aligned to the enhanced traces was accurately reconstructed. The simulation validation result demonstrates that our method can accurately reconstruct the shapes of the defects and rebar with the clear boundaries. Then, as we know that GPR usually move along the tunnel when performing the inspection, then collects data of long survey line. The existing method is divided these data into several segments and use a DNA model to process each segment separately and then splice the result. This may lead to the distorted shapes and inconstant dielectric value in the splice area of the two segments like this. So in order to solve this issue, we proposed a multitask deep neural network that combines CNN with LSTM for permittivity inversion of continuous GPR data collected from a long service line. Specifically, we use a dense unit and bi-convex LSTM to share and fuse information of the several bit-scan segments. Then during the decoder, we design a dual task decoder for simultaneously invert the permittivity distribution and provide us the class label of the defect. Then the simulation results demonstrate that the distortion of defects, the defect's shape and the inconsistency of permittivity value was mitigated, and the defects category and permittivity distribution was obtained. In order to validate the aforementioned method, we built a concrete model, and we deployed some artifact defects in the concrete model to simulate the so-called defects. The result demonstrated that the method can reconstruct the shape of amorphity and the dielectric distribution of the concrete for both water and air defects. We also built a sandbox model that containing artifacts defects for validation. The method has retrieved its final result and provide us the permittivity inversion result and the imaging of the defects. Then I will go to the fourth part. Honestly, the dielectric inversion is more for like the academic uses purpose. But in industry, all we need to know is where is the location, where is the location of the defects and what the location is. So the issue is how to identify the class label and the location of the defects from the GPR image. To solve this issue, we started the deep learning-based subsurface defects identification method. So the challenge is currently there isn't available data set for the GPR image, not like the image, the neutral net image collected by the camera. As an annotation of the GPR image is time consuming. More importantly, annotated GPR image in one tunnel may not be applicable to other tunnels. So the issue is how we can identify the inner defects when the annotated GPR image are unavailable. So we designed a two-stage method. The first stage, we used the unsupervised actual to cynetic GPR image translation work for precision and generate a translated cynetic GPR image. And then in the second stage, we use the DNA model, which is trained only on the cynetic GPR image for identification.
Professor Wang, 3 minutes left.
Okay.
Thank you.
To be specific, for the unsupervised GPR image translation network, it is trained using unpaired actual and cynetic GPR data in an unsupervised manner. And this guy can convert the GPR image collected in real world to the corresponding cynetic GPR image. Then the translated cynetic GPR image retains the characteristics of the defects and keep the style of simulated data. This is followed by a DNA model with a deformable convolutional kernel and a rotational region detection module to identify the category and location of arbitrary oriented defects. The key is we used a deformable convolutional kernel for feature extraction. It can adaptively change the shape of the convolutional kernel according to the shape of the defects, not like the the traditional kernel, which has the fixed shapes. The simulation result demonstrates that not only the category and location, but also the orientation of the arbitrary orientated defects can be detected. Then the method was also tested by the sandbox model, and it can provide us the location and orientation, and as well as the class label of the defects. And the field testing was performed in several journals. The categories, accurate location of the arbitrary oriented defects was identified. These are some results. To conclusion, we have developed a compact GPR and tunnel inspection robot for automatic tunnel detection. And some deep learning based GPR data inversion method was introduced for tunnel structure defects imaging and dielectric property inversion. And GPR image based some subsurface defects intelligent identification method was designed for providing the class label of defects and the location of arbitrary oriented defects when annotated GPR image are available. That's all for my talk today. Thanks very much for your attention. Thank you.
Thank you very much, Professor Wang, for giving us such an interesting topic. And our next speaker is Professor Hongzhan Cheng from Hunan University. The topic is effects of cement on the workability of fresh sand cement bentonite mixture for cut-off wall construction using two-phase method. Hello, Professor Cheng.
Okay, Professor Cheng, can you hear me?
Yeah.
Okay. Can you see my screen?
Yeah.
Okay. Okay, thanks, Professor Cheng, for your kind introduction, and thanks for the ISEG organization committee. Okay, my topic today is effects of cement on the workability of fresh sand, cement, and bentonite mixtures for cut-off wall construction using the two-phase method. This work was done in Nanyang Technological University with Professor Yi. Okay, my presentation consists of 4 parts. First, I will introduce the research background. As we know, the C-phase cut wall with a low permeability is usually constructed in soil, especially in sand layers, to prevent groundwater seepage through for various civil engineering, like dam, dig. Earlier, soil bentonite cut wall had been widely used as insular vertical barriers to prevent groundwater flow. But now, recently, soil cement bentonite cut wall has been used more frequently because it has high strength with the addition of cement slurries. The trace remixing and cutting deep wall (TRD) method is able to create high homogeneous soil cement bentonite cut walls compared to other in-situ mixing methods like the deep mixing methods. In general, for the TRD cut wall, it can be conducted using the one-phase method or the two-phase method, as shown in this picture. In the left figure, it's a two-phase TRD method. For the two-phase method, as shown in the figure, the natural soils is first cut and mixed with the cutting floor in the first phase, and the sand bentonite mixture is remixed with the hydraulic mixture in the second phase. In the first phase, bentonite slurry is tabulous. Bentonite slurry is typically selected as the cutting float, and the cement slurry is usually selected as a hydraulic band. For the one-phase method, the natural soil is cut and mixed with the two slurries simultaneously. For the cut walls instruction in a relatively deep mess or high soil, the construction performed to execute in the two-phase method. Moreover, previous studies were designed for soil cement bentonite cut walls using the one-phase method. There is less knowledge on the two-phase cut wall. So the workability of the wall materials is critical for the homogeneity and the mechanical property of the cut walls, including the UCS and the permeability. And the workability of cut wall materials is commonly quantified using the flowability and the bleeding. In general, a good workability requires a high flowability and a lower bleeding rate. Okay, let's move to the second part of my presentation, which is about the workability of sand bentonite. It corresponds to the first stage of the two-phase TRT method. In our study, two types of sand and two types of bentonite was selected, and the particle size distribution curve that was shown in this picture. And the two sands have different granulometries. We named fine sand and coarse sand in our study. And the two bentonites was categorized as sodium bentonite and calcium bentonite. Based on their liquid limit and strain index results, we can find that sodium bentonite has a much better water retention capacity and straining potential. Okay, to prepare our sand bentonite mixture, the dry sand and the bentonite was firstly mixed in a mixture for 5 minutes, and clear water was added and mixed for another 5 minutes. This process is similar to the first phase of the cut walls construction. Then the workability of the fresh sand bentonite mixture was immediately tested for flowability test and the bleeding test. The flowability test was using the flow table method. The flow table method using standard flow mode and flow spread diameter with the method. Apparently, large flow spread diameter means the higher flowability. On the other hand, bleeding test using 1,000 millimeters cylinder, and the volume of bleeding water was recorded at the 3 hours stating, and the bleeding ratio was defined as the ratio between the volume bleeding water and the initial volume of the water in the cylinder. Okay, next is our results. First, the flowability result is provided. The desired flow spread diameter for construction proposed is between 150 and 230 millimeters, as shown in your pictures. From the next picture, we can see that the diameter for the pure fine sand is below the 150 millimeters. It means the addition of bentonite is required to obtain the workability of flowability. Moreover, the flowability spread diameter saw a linear increase with the increase in the water to sand ratio for the both two sand and two type of bentonite. And compared these two fingers, the flow spread diameter is insensitive to the sand grinding. Okay, here is the bleeding result, in general, the acceptable bleeding water should be less than 3. And it was expected that the bleeding water for both stands was increased by increasing the water to stand ratio. We can also find that the bentonite has the significant effect on bleeding of the stand bentonite mixture, depending the bentonite content and the bentonite type. Moreover, it's clear that the sodium bentonite is more effective to control the bleeding water than the calcium bentonite. So we can conclude that the sodium bentonite is better than calcium bentonite in the condition of workability in the first stage. Okay, the third part is about the workability of sand, cement, and bentonite, correspond to the second stage of the TRT method. Okay, 5 sand bentonite mixture was first selected to investigate the effects of cement slurries. A similar flowability of selected sand mixture is selected, and no bleeding water was observed for these 5 workable mixtures. To prepare sand cement bentonite mixture, the cement slurry was added to the fresh sand bentonite mixture and mixed for 5 minutes. This process is correspond to the second phase of the cut wall construction, and this fresh mixture was immediately subject to the flowability and bleeding test. From the flowability test result, we can find that both the both the effect of water to cement ratio and the cement content, these 2 factors were considered in our studies. Based on the left picture results, calcium bentonite based mixture is more sensitive to the change the water content than the sodium bentonite based mixtures with engagement with the results in the first stage.
Professor Chen, 3 minutes left.
Okay, thank you. Interesting. A significant difference in the flowability for these 2 type of bentonite mixtures, and as shown in the right finger of the flow diameter of mixture increased as the cement content. To better characterize the effect of cement thread, the left finger compared the change of flowability caused by adjacent dry cement and cement slurries. We can find based on the dry cement result, we can find opposite change in the flowability is we can find for the 2 types of bentonite. For sodium bentonite mixture, the flowability increased, but for the calcium bentonite, the mixture flowability is decreased. This formula can be clearly seen from the photo of mixtures after the flow table testing. Here is the bleeding result. The bleeding result show that the bleeding water tend to increase as the water to cement ratio and the cement content for both 2 bentonite types. By comparison, the bleeding of sodium bentonite mixtures was higher than calcium bentonite mixtures with the same bentonite content, because in the first stage for sodium bentonite mixtures, a higher water to sand ratio is selected. Additionally, addition of cement slurry occurs more increase in the flowability and bleeding for sodium bentonite mixtures. Okay, here is about the bentonite cement interaction. Previous studies have demonstrated that cement can chemically affect the hydromechanical behaviors of the cement, behavior of the bentonite, sorry, and the original sodium and in bentonite interlayers was exchanged with the released calcium ions from the cement slurries, result calcium bentonite, and the diffused double layers of bentonite particle was reduced. For select cement bentonite mixture, we conduct the XRD test. The result confirmed the cation exchange between the bentonite and the cement, and this reaction lead to the significant reduction in the work retention capacity and the threading potential of sodium bentonite. And we can also find that this reaction is worked very quickly. Okay, last part is the two main conclusions in our studies. A design of cement would case significant increase in the flowability and the bleeding for sodium bentonite based mixtures in the first phase because of the chemical reaction between cement and sodium bentonite, and the XRD results identified this cation exchange between them. Okay, finally, this study was under the support of IMO in Singapore and the Chinese Postdoctoral Council. Okay, that's all. Thanks for attention.
Thank you very much for your presentation, Professor Chen. Due to the time limit, we cannot have the discussion part. And if you have any questions, you can contact Professor Chen later.
Okay, thank you.
And our next speaker is Dr. Yang Cheng from Xi'an University of Technology. The topic is study on hydraulic mechanical characteristics of layers reinforced by microbial-induced calcite precipitation. Oh, Dr. Chen, yeah.
Okay, can you hear me, Professor Chen? Okay. Good afternoon, distinguished chairman, researchers home and abroad, ladies and gentlemen. I'm Yang Chen from Xi'an University of Technology. It's my great honor to give a presentation here. Today my topic is study on the hydromechanical characteristics of loose reinforced by microbial-induced carbonate precipitation. My presentation will cover the following aspects. First, I will give a brief introduction of the background and the motivation of our research. Loose sediments covers, as is well known, loose sediments covers about 10% of the Earth's land surface. Especially in China, it covers about 6.5% of the Chinese mainland, especially in Western China. And natural loose is famous for its special engineering properties, for its high porosity and water sensitivity. It is easily deteriorated by the increase of soil moisture contents and also the external stresses. And also, loose is a quaternary airline, which is widely distributed in dry areas, and several engineering problems such as the landslide, the tunnel collapse, and the road subsidence or road damage have often occurred without prior treatment of the loose. Hence, it is very crucial for researchers to find possible ways to loose enhancement. There are several loose enhancement reinforcement methods, such as the physical, mechanical methods and chemical methods. Methods are diversified, especially for traditional loose reinforcement methods. Well, they all have some inevitable limitations, especially with the scenario with much focus on the green development worldwide. So it is very crucial for researchers to find some green techniques to reinforce the loss. MICP, by the way, MICP is the initialism of microbial-induced carbonate precipitation. MICP is very popular in recent years, and it is applied to many other soil types, just like sand and expansive soils. And for loose soil, as far as I know, Professor Tang's group also did some pioneer research on the MICP applications in loose soil. In this process, the hydraulic bacteria was injected into the soil and followed by the injection of the salmon reagent solution and also the urea. The bacteria will hydrolyze the urea and then producing carbonate ions. Then the carbonate ions reaction with the calcium ions, and then the calcium carbonate was precipitated, which is solid crystalline materials can bond the soil particles together. And the main purpose of our research is to present some hydromechanical improvements of the MICP on looses. The loose tested in current study was sampled from a set and the Hanjiang to Weihe River Valley Water Diversion Project. And better to know the MICP method is combined with an engineering project. So we also did some field applications. In this topic, I will only introduce the experimental studies. And the different conditions, including the salmon reagent concentrations and also the curing ages, are also considered. And some macrostructure of the loose soil are also observed by ICM test and also the MIP test. First, we did some influencing factors about the MICP. We concluded that the optimal parameters for the bacteria and also the urease activity, the optimal conditions are concluded as the bacterial inoculation ratio of 1% and at a temperature of 30 degrees, and also a pH of 8, and the best and the optimum calcium source is calcium chloride. And based on these basic factors, we conducted further research. We conducted a series of unconfined compressive stress tests to evaluate the effect or the enhancement of MICP on loose soil. From the stress strain behavior, we can see that the largest UCS values occurs at CRC equals to 1 mole, reaching about 720 kilopascal, which is 3.6 times of the plain soil. And also, when the CRC is equals to 1.5, the MICP treated loss was relatively low. It's only 1.8 times of the natural loss, which may be attributed to that because the higher CRC means the faster precipitation of the calcium carbonate, which will block the surface of the loose voids. So which will retard the precipitation process. And also different curing ages are evaluated.
As we can see, when the curing duration increased from 0 to 7 days, the UCS value increased by about 41%. And then for the other 7 days, the average QU value increased by 56%, which can be concluded that MICP method is very good for a very short time enhancement of loss. And also we concluded the relationship between QU and also the calcium carbonate content in different sections of the specimens. We can see there's a large inhomogeneous into the soil specimen, which is also a very crucial questions for the enhancement of MICP treated loss samples. And also the QU of sand and loss both increase linearly with the calcium carbonate content. For the same retention period, higher QU values were obtained with higher calcium carbonate content. So this is the stress parameters of the MICP treated loss, and also for the stiffness of the loose soils. What about this? So the deformation modulus was defined as the ratio of the stress corresponding to half failure strain to the strain which can represent the stiffness of the soil. As we can see, the deformation modulus of solidified loss also exhibits a substantial increase with the curing ages. And also, an empirical equation can be concluded, which indicates that both the stiffness and the stress MICP treated loss are increased. And for the hydraulic properties of the MICP treated loss, we can see we conducted a serious test about the disintegration rate. And we can see from the propagation of disintegration rate curves, it can be divided into 3 stages. The initial stage, the loose sample was first immersed into the water, and the disintegration ratio almost keeps constant. The loose sample keeps intact. And the second stage is a rapid disintegration stage. The loose structure damage rapidly, and the loose particles falling quickly from the specimen body. And then move to the last stage is a stable stage. There are only some insoluble minerals remains, and the spalling retarded very significantly. We also plotted the disintegration rate with various CRCs and different curing ages. We can see that the final disintegration ratio of MICP treated loss can decrease at a maximum rate of 63.3%, which means compared to the untreated loose specimen, not only the disintegration ratio was decreased, the disintegration process was also prolonged. We also did the permeability coefficient based on the variable height permeability test. As we can see from the figure, the permeability of MICP treated loss gradually decreased with curing ages, and it can decrease more than 2 orders of magnitude with the curing age. So, and for the third property of the water sensitivity is the collapsibility. Well, as we all know, for collapsible soils, it is very sensitive to water, especially for loss. So the collapsibility test was conducted. And as we can see from the statistics, the average collapsibility coefficient of the 3 soil samples decreased by about 23.8 after a curing age of 14 days. So and further, we also conducted some microstructure tests at the microstructure test electron microscopy images are listed here. As we can see, without MICP treated loose particles, the surface of the loose particle is very smooth. And with the injection or the participation of the MICP treatment, some of the cement aggregates are accumulated between the loose particles, and the loose voids was filled by the calcite crystals, which can bond the soil particles together. So the calcium carbonate precipitation plays the role of filling, cementation, and blogging, which can increase the integrity of the samples. So that's all of the presentation, and some conclusions can be drawn. So from our research or from this report, we can know that the maximum enhancement in shear stress was achieved when the loose sample is treated under a cement reagent concentration of 1 mole, curing for 14 days, and compared to untreated loose, the uniaxial compressive stress can be increased by 3.6 times. And also for the UCS values of MICP treated loose, it roughly the maximum increase is about 3.6 at curing age of 14 days. And as we concluded, the MICP is good for short-term curing to increase the loose stress. And also for the calcium carbonate precipitation can bridge and bind the voids between loose particles to improve the shear resistance of MICP treated loose. And it can effectively reduce the disintegration rate of MICP treated loose. And also we conducted some field tests, and maybe hope I can have the future chance to share with you guys now. And thanks for your attention. I'm so sorry. Can you hear me now? Sorry for the internet.
It's okay. Thank you very much for your wonderful talk. Thank you.
Okay, thank you, Mr. Chen.
Okay, our next speaker is Dr. Hao Wenguo from the Hong Kong University of Science and Technology. His topic is a novel eco-geotechnical earthen cover system using recycled construction waste. Let's welcome Dr. Guo.
Thank you, Professor Chen. Is my voice clear?
Yeah.
Okay, thank you. Thanks for Professor Shi and Professor Tang, and also the organization committee of this symposium. Today, I would like to share you with our latest research. I collaborated with Professor Charles Ng on the sustainable development of cover system by using the recycled construction waste. First of all, I would like to introduce the background information, followed by the research strategy, methodology, and some key findings. Finally, I will draw some conclusion. Currently, nearly 2,000 sanitary landfills and more than 5,000 simple landfills exist in China. The degradation of solid waste pollutes the surface and groundwater, produces odor gas, so that the safety and the long-term reliability of landfill has become more and more important. So nowadays, we also face the challenges of cities saved by solid waste. Nearly 3 billion tons of construction waste produced per year. The storing of construction waste is prone to affect the safety of the infrastructures. According to the closure standards, there requires a fan cover system to minimize the leachate generation, gas emission, as well as to prevent the groundwater contamination. Geomembrane is selected as a material to build a fan cover system for modern landfills. However, the use of geomembrane easily induces interface stability problems, and it also easily affected by the defense holes and durability of geomembranes. So that the using of geomembranes would definitely increase the maintenance cost of the closure of the landfill. It shows in the bottom 3 figures, several billion of US dollars was caused, financial losses was caused due to the failure of geomembrane. So in order to solve the problem taken by geomembrane, alternative cover assessment program led by USBA was carried out in since 1998. Since then, many alternative covers were proposed and investigated. However, those covers only perform well in the arid and semi-arid regions and only sustain and small rainfall of humid climates. Therefore, a 3D landfill cover system was proposed by our group. The cover can work that combines the benefits provided by the upper capillary barrier and the bottom low permeability to prevent the water percolation as well as the gas emission. Previous laboratory tests and field tests have proved the effectiveness of the landfill cover system and humid climates, and also the elimination of the use of geomembrane. But the performance of the landfill cover system using recycled concrete is still unknown and need to be further studied. So to tackle the limitation, this study proposed a multi-dimensional research program including the 1D soil column, 2D flume test, field monitoring, as well as numerical analysis. This slide shows the material property we used in the physical. Fine recycled concrete used as material for the top layer, coarse recycled concrete used for the middle layer, and we get inside used for the bottom layer. From the bottom table, we can find that those materials have very high contrast in permeability, so that it can ensure the performance of the cover system. The 1D test includes 2 soil columns. Each of them combine a 0.4 meter top FRC layer, a 0.2 meter CRC layer, and a 0.4 meter refused soil layer. We also installed 10 centimeters and a moisture probe to measure the soil suction and volumetric water content changes along the soil. The top boundary of those 2 columns, we set a 0.1 meter constant water height for last for 8 hours to simulate a 16-year return period rainfall of Hong Kong. The bottom boundary was specified as free drainage. This slide shows the mirrored and computed variation of matrix suction in those 2 columns before and after ponding. The mirrored results, the numerical results match the computer results reasonably well. We can find that before the ponding, the initial suction in the grass column is larger than that in the bare one. This is mainly due to the evapotranspiration induced root water uptake in the top layers. The high initial suction corresponds to the lower permeability. It can reduce the water infiltration during the ponding. So after the ponding, the mirror matrix suction in the bare column reduced significantly, whereas a relative high suction, such as the 0.1 meter and 0.3 meter in the grass column, was preserved. So this shows that after rainfall with a return period of 16 years, the capillary barrier in the grass column is still active, while that in the bare column is failed. The results show that the effect cover system using the cell concrete can enhance the performance of the cover. Use the instrument of the flume model from the right-hand figure. We can find that in order to simulate different rainfall conditions, a rainfall simulator was developed and installed above the cover system. By using this simulator, the rainfall intensity and duration can be regulated. In this study, the rainfall return period is fixed at 100 years in Hong Kong. A return duration was changed from 4 hours to 12 hours. The inclination angle of the cover system was changed from 3 degrees to 18 degrees according to the national standards. 10 centimeters and 1 soil moisture probe was also installed in the flume. In this study, we mainly presented the manual results in the middle section. And also, we also installed a train gauge and some other equipment to measure the water balance component during the test. So this slide shows the left-hand figure shows the comparison between the mirrored and computer soil suction profile during the simulated rainfall. The total depth during the 12-hour rainfall was more than 400 millimeter. As the heavy rainfall studied, the soil suction near the surface was the first to be influenced by the water infiltration, whereas the matrix suction in the middle CRC layer and the bottom layer was not changed after the fall of the rainfall. So with the rainfall continued, lower soil suction returned in the shell depths. This reduction of the suction means the breakthrough of the competitive barrier formed by the top two layer of the soil concrete. At this point, the function of the middle layer can transfer from the barrier break to a drainage layer, so that it still can function to reduce the further infiltration into the bottom layer. And from the right-hand figure, we can find that during the initial stage of the rainfall, that means 0 to 6 hours, surface runoff and soil water storage increase linearly as the rainfall continues. But the amount of water storage reached its maximum value at 6 hours. So after that, the infiltrated water started to divert laterally in the top FRC layer and the middle CRC layer. This means that the top two layers can function as the drainage layer effectively. During the whole test, no population was observed, even without using a gel membrane. This slide shows our physical test conducted under different rainfall duration from 4 hours to 12 hours, and different inclination angles from 3 degrees to 18 degrees. We can find from the right-hand figure, from the left-hand figure, the longer the rainfall duration, the more water will be infiltrated into the current system, so that less surface runoff under the longer duration, and less soil water will be over, as well as the lateral diversion. And the intensity will also reduce in a sooner water breakthrough of the top competitive barrier. From the observation for the different inclination angle, surface runoff increased. Can find that surface runoff increased with the increasing of the angle, and the increasing of the angle will also lead to the reduction in the water storage as well as in the lateral diversion. We also carry out some parameter studies to optimum the combination of the particle size we used for the current system before we use them in the field site. The top left figure shows that the surface runoff decreased sharply due to the D10 of FRC increases from 0.1 millimeter to 0.5 millimeter. So with the first improve of D10 of FRC, the surface runoff reduced gradually to 0, but the rainfall water into the landfill cover would transfer to water storage and infiltrated water into the deep soil layer. As shown in the figure, the surface runoff reduced to less than 15% when D10 of FRC larger than 0.2 millimeter. This meets the recommended criteria by the national standard for the surface runoff of Greenland. However, the D10 of FRC does not influence on the returned and diverted water when the FRC D10 is larger than 0.5 millimeter. So the D10 of the top FRC layer is suggested within the range of 0.2 meter to 0.5 millimeter. As shown from the top right-hand figure, the surface runoff increased with the improvement of the D10 ratio between the FRC and CRC layer from 10 to 100. The reduction in the returned and diverted water is very solid when the D10 ratio increases from 10 to 15. It can be found that the surface runoff returned and diverted water is almost not changed when the D10 ratio increased more than 100. So as a result, the D10 ratio between FRC and CRC layer is recommended as 15. those combination can provide sufficient return at the oil water as well as meet the design criteria. And we also conduct a numerical parameter study on the bottom FRC. In this study, we want to replace all the soil layers in the cover system using FRC. We found that if we want to achieve a better performance to meet the US EPA guideline, the D10 of the bottom FRC is less than 0.02 millimeter. So based on the previous physical test, okay, thank you, as well as the numerical parameter study, we came out of this particle size combination. The top layer we use a coarser FRC. The middle layer we use a coarser CRC. Because for the supplier producers to produce very fine FRC is not credible and also not economically efficient. So we use the 10% bentonite to amend the FRC used as a bottom layer. Here is the instrumentation layout as well as the front view of our field site in the Shenzhen field. We also installed meters, some moisture probes, and gas pressure sensors, as well as lysimeter in the field site. The whole field site is around 300 square meters. This slide I will show some construction produce of our field sites. The top one is the bottom layer, the middle layer, as well as the top layer, and also our installation process about the lysimeter, the movement point, as well as the soil moisture probes. So this slide shows the monitor result on the population. Top figure shows the cumulative one during the around 2 years monitoring. We can find that the whole the cumulative population during the 2 years is less than 30 millimeters and definitely lower than the US EPA standards for the 2 years. And the first year population is nearly 0. The second year is close to 6 millimeter. And we also compare the annual population with other type of the cover system, like the capillary barrier, the ED cover, and also our previous studies, so that we can find that when the annual rainfall larger than 1,500 millimeter, the performance of the cover system using RCA is better than other type of the cover systems. And I draw some conclusions. Find the beneficial of the grass and also provide the recommendations for the particle combination of the cover system. And the way forward, because of the cover system, the function of the cover system is built on the unsaturated, essentially on the particle size and the hydraulic property of the materials, so that all the materials can crush into the suitable particle size can be used as a material in the cover system, so that the real bricks, the grass, as well as the fine fraction of the aged municipal solid waste can also be used in the cover system, because those waste materials are in very large amounts, but their strength is not high, so that it can not be recycled in the construction engineering, such as the road and the buildings. And we also have some other application scenarios, such as the slope stability systems. Our cover system can combine with the plants, as mentioned previously by Professor Liang, and we also localize the green system for the sponge city. So that's all my presentation. Thank you for your attention.
Thank you, Dr. Guo, for your presentation. And that's all of the presentations in this afternoon. Ladies and gentlemen, please do not log out of our Zoom meeting room. Following is the closing and the awarding ceremony chaired by Professor Chao Shen-Tang.
Okay, ladies and gentlemen, good afternoon, good evening, and good morning. This has been a wonderful 2 days. Now I'm very happy to host this close ceremony. Okay, the first event we want to announce is about the HY Farm Best Paper Award. First, I want to introduce about this award. Professor HY Fan kindly donated the funding to ISEG, and the best is where this funding is for the establishment of Best Paper Award at ISEG International Symposium. The HY Fan Best Paper Award will have 5 awardees, with 1 champion and 1 first runner-up and 3 honorable mention. So the candidates should be among the speakers, and their age should be no more than 38. The procedure for this award is the awardees are selected by all ISEG council members through first based on their abstract and the presentations. I just get the result from the conference organization committee, and now I want to announce the winner of this HY Farm Best Paper Award. The champion is Kai Gu from Nanjing University. He got 12 votes. And the first runner-up is Okay, the first runner-up is Qin Chen from Nanjing University. She got 10 votes. And the honorable mention, there are 3 people. One is Junjun Li from Southeast University. He got 9 votes. And the second one is Ji Yingfang from Queen's University. He got 6 votes. And the third one is Alexander Ludek, comes from Technical School, Georgia Agricola. He got 5 votes. Congratulations to these 5 awardees. Now, I want to say some about our this symposium for the end of this event. For this symposium, we have around 60 speakers from North and South America, Asia, Oceania, Europe, and Africa. The topic covers a wide range of aspects in environmental geotechnology. I think all of us enjoyed the talks, and many of us got inspired by these exciting works. Although online, it is a good time to make friends and build up connections. I would like to take this chance to thank all the speakers for their valuable time. Your wonderful talks make this event a big success. I would also like to thank the guests and the participants. Thanks for your support to the symposium. I would like to thank all the organized committee members and the volunteers for your hard work to prepare for this event during the past few months. Environmental geotechnology is a promising subject with a bright future. The challenges and opportunities are still here. And our mission is not completed yet. Let's work together and move environmental technology forward. We look forward to your continued support. Thank you, and see you at our next event. Thank you all. Hopefully, see you soon. Bye bye.